the Steenrod problem is a question about when a fixed singular homology class can be realized as a continuous image of a fundamental class of a closure-oriented manifold. And here there is a very important result which was mentioned in the talk of Babenko, that it's not very hard to see that any homology class can be realized by the fundamental class of pseudo-manifold. And this fact allows us to work in some, instead of work in the whole category of topological spaces, we can work in some nice category. And so from this moment, I will work in the category of pseudo-Abelian complexes of finite type, but all the results will be true in the whole category of topological spaces. And also, in modern language, Steenrod problem is equivalent to the description of the image of natural transformation from oriented Bordisms to homologies. So its morphism look like, so you have and here, the element here is pair of a manifold and a map, where f from b to x, and such an element goes to direct image of fundamental class of the manifold beam. And so it's also very natural to study the corresponding problem in complex case. So we want to give some description of image from complex Bordisms to homology. So there are some very classical results. First result was obtained by Tom, and it states that if dimension is small enough, then this map is always surjective, and so any class can be realized by oriented manifold. But in higher dimension, it's generally not surjective, and you have non-realizable classes. Also, there is another theorem of Tom which states that there exists some number, positive, which depends only on dimension, such that after multiplication by this number, any class became realizable. And similar theorem holds in a stably complex case. So after the theorem, it's natural to define KSO of n as minimal such A of n, and we define KU of n similarly. So it's minimal number such that after we multiply a homology class by KU of n, it becomes realizable by stably complex manifold. And there are two natural problems after the theorems. First is to find some good coefficient, sufficient condition for realizability, because actually it's very hard to construct some class which is not realizable. And second is, of course, to compute these numbers KSO of n and KU of n. So for the first problem, the very good answer was given by Sergei Petrovich Novikov. Namely, he proved the following theorem, that if such homology groups, so you take n minus 2r times p minus 1 minus 1, are p torsion free, where p is this, for any odd prime p and any r greater or equal than 1, then any n-dimensional class can be realized by oriented manifold. So in other words, abstractions for realizability of n-dimensional class lies in p torsion of such groups. And nice corollary is that if your homology group doesn't contain odd torsion, then any class is realizable. And if your homology group's just torsion free, then any homology class can be realized by stably complex manifold. And there's some nice corollary, for example, for Grassmann space, you know that is true. So when you take real Grassmannians, then it can have two torsion, but it have no torsion, and any classes can be realized by submanifold. And in stably complex case, when you consider complex Grassmannian, they have no torsion at all. Yeah, and some remarks that this condition is actually in some sense the best with respect to its strength and computability. So it's very easy to compute, and it's, yeah. Then let us discuss about numbers, KS of n and KU of n. So first important remark is that geometric bounds for these numbers are actually multiplicative. It means the following, that if you know that any class can be realized after multiplication by some number A, then A is divisible by K of n. And again, if you can construct a class such that after multiplication by A, it cannot be realized, then K of n is divisible by A. And it follows from the fact that realizable classes form a subgroup in homology. So it's natural to write bound not for KSO of n and KU of n, but for degree of primes in the prime factor decomposition of them. So we introduce notation nu p of A will be degree of P in the prime composition of A. And here are two important theorems. First by Novikov, it states that KSL of n is odd, so nu2 of it is 0. And theorem of Brown and Peterson, which states that for odd primes, nu p of KSO of n is equal to nu p of KU of n. So KSO of n is just maximal odd divisor of KU of n. So from this moment, we will be interested only in KU of n. Then there is two important theorems. First theorem of Buchstaber. There is a formalization, but let me draw what is going on in it informally. So here you have homology groups of X. Here is dimension M, where you want to realize your classes. And the condition is the theorem that you can have abstraction in the Novikov sense up to dimension f minus n. So we can have abstraction. And here we have no abstraction. Yeah, in Novikov sense. So these groups have no p torsion. Then it states that if you take class here, then it can be realized after multiplication by this number. And moreover, this estimate is exact in n. So it's exact in n, not in m, but in n. And this theorem actually can be reformulated just so. This case of n, you can ask this, the analog of Steenrod problem in stable homotopy category, and then this KSU of n will be just answer to the multiplicity in the category of spectra. And also there is similar theorem of Brunfield, but the condition is the theorem that you have nothing. You have nothing. So your space is just m minus n connected. So corollary of theorems of Buchstaber-Brunfield is that you have these inequalities for the number nu p of KU of n. So upper bound is n minus 2 divided by 2 times p minus 1. And it's just straightforward. And this bound follows from exactness of their boundaries in n. So after this result, you see two problems. First, we have obviously some gap between upper and lower bound. And moreover, for n equals 6, from this bound, we can't recover Thom result. So for n equals 6, we have abstraction actually in 3, because 6 minus 2 divided by 2 times 3 minus 1, it's 1. And now I can state my result. So it states the following boundaries for this number nu p of KU of n. So upper bound is very similar to Buchstaber-Brunfield bound. So we just, instead of 2 here, we have 3. Sorry, we have 3. And lower bound is very different. So let me discuss something about lower bound. So first corollary is that KU of n is divisible by n minus 1/2 integral factorial, and it just follow from the Legendre theorem that states that nu p of n factorial is just sum of n divided to p power I. Yeah. And so these numbers are just powers of p in prime factorization of these numbers, of this number. Second observation is that if n some special, so it satisfies this inequality for some natural t, then upper and lower bound in the theorem coincide, and you have just exact value of nu p of ku of n. So you have infinite series of dimension in which we have exact answer, but the problem is that these series are different for different primes p, and they cannot be glued just in silly way. So we have no infinite series of dimension in which we know the answer just for ku of n. And third observation, that the difference between upper bound and lower bound is actually very small, so you can bound the difference by just logarithm, p logarithm on n minus 1/2 plus 1. Yeah, and so the ratio of the upper bound to the lower bound tends to 1 and tends to infinity, and actually very quickly, because it will be just plus, it will be 1 plus logarithmic function divided by linear function. And so it goes to 1 very quickly. It is first theorem. And second theorem states that if n is sufficiently small, then the lower bound for nu p of ku of n is exact. In particular, if we take p equal 2, then this number became 12. And so we obtain that if n less than 12, then ku of n is just n minus 1/2 integral part factorial. And if p equals 3, then this number is 24. And we obtain that KSO of n is just maximal odd divisor of n minus 1/2 integral part factorial. Okay, and here is the table of these numbers, but it's just some computation. And if n is 24, then I don't know, it is like this or 3 times this. Okay, now let me say a few words about proofs. So first, let me remind that we have the following theorem, which is like Pendragon Tom and some Alexander duality, that a class of a finite value complex S is U-realizable if and only if there exists a map from Alexander dual of X to mu n minus n minus 1, such that pullback of fundamental class of this space is Poincare dual to X. From this, one can see abstractions to realizability. In particular, if we will take integral Steenrod operation, what does it mean integral? We take mod p Steenrod operation and we compose it with Bach-Stein operator. Then if this operation acts on X by non-zero, that X cannot be U-realizable. Yeah, it follows just because on U, all integral Steenrod operations act by 0, since integral cohomology of Tom space it doesn't contain p torsion. It actually they torsion free. And so and so the idea. So in order to construct non-realizable classes, we should just construct a homology class on which some Steenrod operation acts non-trivially. And this problem can seems to be easy, but it's not easy, since you have actually no universal homology class. So homology functor is not representable, so it's very unclear how to construct a homology class of small dimension as possible on which some Steenrod operation act non-trivially. It's not a trivial problem. And in order to do this, there was, in my opinion, some ingenious idea of Tom. So he proved the following duality theorem for action of Steenrod operation on homology and cohomology. So if you have some space X, you have homology class and cohomology class, and you have some mod P Steenrod operation, then the following formula hold. You can pair X with theta of Y, or you can pair Y with action of antipode of theta with X. And then this pairing will be equal. The very nice corollary is following that if you have trivial rational homology, trivial rational homology groups, and you have cohomology class such that Steenrod operation, this Steenrod operation is not zero, then for any homology class such that this pairing is non-zero, we have that beta theta of X is non-zero. And moreover, you can always find such a class X. So these conditions come from the fact that we should control some integral stuff, like we should control that Bach-Stein is not zero. And in order to control it, we need this condition. And just using this corollary, Tom constructed his 7-dimensional non-realizable class. And it's actually a class in H7 of K Z over 3Z to Z. Yeah, it is such class that pairing of A with P13 beta P iota is non-zero. Yeah. So just using this duality, he constructs such operator. Moreover, using this theorem, he proved that if A is 6-dimensional class, then beta P1 on A is 0. And so you have no abstraction in dimension 6. It's also non-trivial because this operation, the value of this operation, this class, lies in H1 of XZ, and this group can contain 3 torsion. But using duality, you can prove that it's non-trivial. Sorry. Yeah. But the problem with this approach is that Steenrod operations has always degree P. So if we take class P times X, then all Steenrod operations will act by 0 on it. Yeah, because they all have degree P. So by this method, we can't prove that such class is not realizable. On the other hand, we of course knew all series of abstraction to realizability. Namely, we have Atiyah Hirzebruch spectral sequence for complex Bordisms, yeah, like this. And we have the natural homomorphism from mu n of x to homology. Infinity and 0, it is factor group of Bordism group. Then you can embed E infinity to E2, and it's isomorphic to homology. And this composition actually coincides with realization homomorphism. So very easy corollary. So realizable classes are actually classes in which survives to E infinity, to infinity page. And so class is realizable if and only if all differentials in Atiyah Hirzebruch spectral sequence for complex Bordisms vanishes on X. And so the idea was to try to mimic Thom techniques, but not for Steenrod operations, but for differentials of Atiyah Hirzebruch spectral sequence for complex Bordisms. But of course, the problem is that Atiyah Hirzebruch spectral sequence for complex Bordisms is extremely hard because grading component of zero of point grows very fast, and it's really hard to control them. So what is easier is to use differentials of Atiyah Hirzebruch spectral sequence not for complex Bordisms, but for complex K theory. So first, very easy proposition is that if you have a homology class and it's U realizable, then all differentials in Atiyah Hirzebruch spectral sequence for complex K theory vanish on X. And it's true since they vanish on fundamental class of MU. And thus, also differentials in Atiyah Hirzebruch spectral sequence for complex K theory are abstraction to realizability. They are not sufficient. They're not sufficient, but they're all abstraction. And also it is very convenient in this approach to think about differentials in spectral sequences as about partially defined multi-valued homomorphisms. Namely, your R list of your spectral sequence can be written as cycles group factored by boundary group, but both these groups are actually subgroups in homology. And so your differential, so your differential is just homomorphism from A over B to A prime over B prime. And of course, you can reconstruct it from A to like, and this whole lies in some group C by C over B prime. Because if you have map from factor group, then you have continued to the whole group. Yeah? And so we can think about differential as about homomorphism from a subgroup in homology to this homology group to a factor group of this homology group. And also, since both elements act transitively on rows of Atiyah-Hirzebruch spectral sequence, so Atiyah-Hirzebruch spectral sequence for complex K-series, it's very symmetric. We can change rows. Then it follows that differential for difference T coincides. Also about Atiyah-Hirzebruch spectral sequence for K-series, we have two very nice theorems of Viktor Matveyevich. First says that if you localize it on P, then these differentials vanish unless this condition. And second theorem states that such differential is always defined on the class P power R minus 1x, and it always contains this operation. So having in mind the first theorem of Buchstaber, we can define higher cohomological operations phi r like this, which will be corresponding to the differential, this differential and this differential in the Atiyah-Hirzebruch spectral sequence for complex K-theorem. Also, so let me remind you, then Tom theorem was duality not for integral Steenrod operation, but for mod P Steenrod operation. And it's actually very smart. So we actually should take the non-integral part of this operation, and it can be done. So we can construct operations phi r tilde, which map us to cohomology with coefficients Q factored by Z localized in P. And we will have equality that phi r is B tilde phi r tilde, where B tilde is Bach-Stein homomorphic for such short exact sequence. And then we can prove the analog of Tom duality theorem for Steenrod operation. So it's really analogous. So we have duality that phi r is defined on some class if and only if this class paired with indeterminacy of operation by 0. So it's like some condition on X, and this is some condition just on pairing. This is the same statement, but for homology classes. And second statement is just the duality theorem, for it states that if phi r is defined on classes X and Y, then we have this equality, and this is correct equality of the element of Q over Z localized in P. And we can obtain corollary, which is very similar to the corollary of from Tom duality theorem. So namely, if you have a CW complex such that its rational homology group is 0, and you have a cohomology class such that phi r is defined on Y and this condition, then there exists homology class X. Then for any homology class X which defines this pairing, phi r will act non-trivially on this class, in particular this class, will be not realizable. And moreover, using this condition, you can prove that such class A always exists. So this theorem is very, very similar actually to this corollary from Thom's theorem. And having in mind this theorem, it is, and very important remark, why is this so useful, that actually you have a universal class on which phi is defined. So as always, if you have some functorial condition on cohomology, then there always exists some, it is in some sense, it's always representable, and you have the universal class on which this condition holds. And so, and so it is very obvious what we should do next. We should just take a universal class on which phi is defined. We should kill rational homology of the space, and we should compute when this Steenrod operation acts non-trivially on this class. And that's it. So the corresponding representable space looks like follows. We can take the spectrum which represents the connective complex K-series localized at P. Then we can take its 2s minus 2 stage of the Postnikov tower, and then we can represent it as omega spectrum and take its Q terms, and then the universal class on which phi is defined will lie in homology group of such space. Then let us kill rational homology of this space. Let us define it by this, and then we should compute when some Steenrod operation acts non-trivially on the universal class of this space. And these computations leads us to these coefficients. So it's very important that these numbers actually comes from computation in Steenrod algebra. So we just should to compute when this operation phi of PR acts non-trivially, and we obtain such numbers. So how many times? Okay. Yeah, and that's it. That's just it. That's an example. And also, it is some comment about this work that actually all the methods are like methods of algebraic topology of 60s. So I don't use any modern methods in the paper. And the really new idea is this duality theorem, that you can write some dualities for differentials in a Hirzebruch spectral sequence. And so it's natural to ask it's important. Thank you. It's important comment that of course this equality will be true just for phi. It will be true, but it will be empty. Because for phi, this pairing will be identically zero, just identically zero, because X is integral class and these guys are integral torsions class. So this will be true, but it will be useless. And after taking non-integral part, it is useful. But it's important that this theorem actually holds in very generality, and what we essentially use is following: that in the assumption of our theorem, first of all, you have symmetry for this high operation. So phi tilde is defined on a class X if and only if the previous one defines and acts trivially. So you have this theorem, this symmetry, and the interdeterminacy of phi is just union of images of action of previous operation phi minus 1 on the class of corresponding dimension. So as like in spectral sequence. Second very important property is multiplicativity. So it follows from just multiplicativity of spectral sequence. So if you have two classes on which phi is defined, then phi tilde is defined on their product, and you have such an inclusion. And third important condition, that your pairing should have some geometrical meaning. So this theorem, it is really about some pairings, and you need to have that these pairings have something to do with geometry. And in topology, it's actually have something to do because you have some duality map from sphere spectrum to smash product of X with its dual, such that new star of product is just pairing. And actually, just applying these three properties of phi, you can prove this here. So moral is that you somehow construct some series of partially defined multi-valued homomorphism which satisfy this property, then you can probably prove an analog of the duality theorem. So, for example, maybe it can be useful for computing Lirassier spectral sequences. Your fiber is like CP infinity, or this theorem is true if you replace K theory by some integral analogs of Morava K theory and something like this. Yeah, thank you very much. Thank you.
So, any questions?
Okay, maybe a naive question, but what if you consider a cohomological version of Steenrod's problem, like a map between usual cohomology and oriented cobordism?
Yeah, then as was proved by Viktor Matveevich, you have a class, universal class in KZ3, and it can be realized with any multiplicity. So you have a map from so three-dimensional bordisms to yeah. And this class is not in the image with any multiplicity. So you have not the analog of such theory.
Okay, so there is no like global duality.
Yeah. Because it's very important that, thank you for the question, it's very important that when you consider the Atiyah, so let here will be homological Atiyah Hirzebruch, and here will be cohomological Atiyah Hirzebruch. Then what is going on? Here you have differential in this direction, and so you have only finitely many differentials. And here you have differential in this dimension, and so you can infinitely many differentials. And this is the case with KZ3. You actually will have infinitely many differentials, infinitely many non-trivial differential in this class.
Thank you.
More questions?
Дорогой Вася, большое спасибо. Ты меня очень порадовал. You, Vasilii, mentioned my result, but let me inform you, it is my result from my PhD thesis. In the time when I started in this area, I was 25 years old, maybe 24. After 25 years, when my teacher, Sergei Novikov, started give lecture in Berlin University about this problem. And very soon, he mentioned to me, Vitya, I understood I cannot find in Maryland University student who can using such technique. And Novikov start to find more simple problem, which using not so many technical, not so many ideas. And now I understood that in Russia, there is a very nice student of Alexander Gayfulin who perfectly using this technique and obtain very deep result. But about realization cycles, in that moment, there was famous Atiyah Hirzebruch problem. What does it mean? Exactly, it related with case KZ3. You know, sorry. Sorry. Yes. But Vasilii mentioned it. You can demonstrate effects in the term of complex case theory because follow the Riemann-Roch Conner-Floyd transformation, you can transform effects from complex case theory to complex cobordism. So it was exactly the problem Atiyah Hirzebruch. You're right. They asked not complex cobordism. They asked about vector bundles. Sorry, you remember? Sorry. What's the question? You see, we have such very nice space. Eilenberg-MacLean's plane KZ3. If you consider the cellular decomposition, we have the points. Next, it is a S3. And we know that, of course, we can construct non-trivial complex vector bundle if you go to suspension. Using the Bott theorem, you have complex non-trivial complex vector bundle here. Okay. After that, we can continue point S3. After that, you can consider X4, X5, and so. It is a skeleton, 4-dimensional, 5-dimensional, and so. And of course, all this skeleton has 3-dimensional homological class. What's the problem? Other vector bundles, this, such that restriction on S3 give this both classes. It was the problem of Atiyah Hirzebruch. I think it was one of the first my paper. We do this with Sasha Mishchenko, and you know this result. It turns out, no, from this concrete class in cohomology H3, KZ3, Z, which is Z, there are infinitely many non-trivial differential. You see? So exactly what such kind of spaces, it is a polygon for finding non-trivial differential, and it is a very surprising case. And what we obtain from your result, certainly it is very interesting to continue what I am doing. You see, you have, for example, KZ3, and start from Atiyah Hirzebruch spectral sequence. E2 term, it is a homology. And for any P, we know how look the differential, you know. So you can calculate next term. And as in my paper, I calculate this. But after that, you go for the next term where you have cycle of differential on the next step. It will be very interesting to calculate. You see, what, for example, in the case, simplest case, P is 2. You see, P is 2. We know what is mean E2. We have differential non-trivial D3. So we can consider E3. After that, you can ask how looks this. And this step I calculate. And for many years, it was surprise for me that Witten, where he considered some problem from mathematical physics, exactly mentioned this my result about D5. It's very interesting. Consider this as universal object. Calculate not all case theory, but calculate how look the term E3, E4, and so on. If we find a good answer, it gives to us some universal model. But let me repeat, exactly in the case is differential next after the 3, it turns out was important for Witten calculation in some related for index problems and so on. So what that's my recommend. Maybe it's interesting to, you see, not, you know the answer, how look, you know, complex cobordism of Einberg-MacLane space, cobordism, you know how look this complex cobordism, how look this K-theory, but interesting, if it's possible by setting, calculate it E K terms. If you will be happy you obtain this result, you obtain with some interesting algebraical object. Thank you.
So that's all for today. Let's thank the speaker again. So we can go home or for dinner. The transfer is